Welcome to tonight's journey into the deep ocean. Close your eyes and let your breathing slow down. Release the tension from your shoulders and your neck. Tonight we travel far away from the busy world. Our destination lies hidden beneath millions of tons of water. We are visiting a legendary site of scientific discovery. Our destination tonight is the famous Galapagos Rift. It holds a special place in oceanographic history. Here, scientists found the very first hydrothermal vents. Before this discovery, the deep sea seemed entirely barren. We will explore this quiet, alien landscape together. Let your mind drift as we begin our descent. We start our journey in the vast Pacific Ocean. The surface waters here are warm and gently rolling. We are located just north of the equator. The exact coordinates are 0 degrees 48 minutes north. Our longitude is 86 degrees 5 minutes west. This places us roughly 200 miles east of the Galapagos Islands. The night sky above us is filled with bright stars. A cool maritime breeze sweeps across the dark waves. But we will not stay on the surface for long. Our path leads straight down into the abyssal depths. Imagine yourself safely enclosed in a deep submergence vehicle. The heavy steel hatch closes with a reassuring seal. We slowly slip beneath the rolling ocean waves. The water quickly transitions from deep blue to indigo. Sunlight struggles to penetrate this dense aquatic medium. At 200 meters down, the light grows very dim. We are passing through the oceanic twilight zone. Marine snow begins to drift past our thick acrylic viewport. These tiny organic particles fall constantly from the surface above. They look like gentle snowflakes in a winter storm. By 1,000 meters, all solar light has vanished. We have entered the midnight zone of the ocean. Absolute darkness wraps around our descending submersible craft. Only the steady hum of our thrusters breaks the silence. The temperature outside drops rapidly as we sink deeper. It stabilizes near a chilling 2 degrees Celsius. We continue falling through the endless black water. Our depth gauge slowly ticks past 2,000 meters. The immense volume of water creates an isolated world. Finally, the sonar indicates the approaching ocean floor. We engage the vertical thrusters to slow our descent. Our powerful external lights pierce the eternal darkness. We hover gently just above the rugged bottom. The exact depth is 2,500 meters. This translates to roughly 8,200 feet. The physical environment down here is incredibly extreme. The hydrostatic pressure is truly difficult to comprehend. It measures about 250 atmospheres. This equals 3,600 pounds per square inch. Such force would instantly crush an unprotected human body. Our titanium sphere keeps us perfectly safe and comfortable. We are floating above a major tectonic plate boundary. This geological feature is known as a mid-ocean ridge. It forms the border between two massive crustal plates. To the north lies the expanding Cocos tectonic plate. To the south sits the massive Nazca tectonic plate. These two rigid slabs of rock are slowly pulling apart. They separate at a rate of roughly 50 millimeters annually. This divergent boundary creates a deep valley on the seafloor. The valley stretches for hundreds of kilometers across the ocean. We are positioned directly inside this central rift valley. The terrain below us is a testament to volcanic power. In other areas, the lava erupted much more quickly. These rapid eruptions form flat, expansive sheet flows. The sheet flows resemble a paved black asphalt road. Occasionally, we spot collapsed pits within these flat plains. These pits formed when lava drained away beneath the crust. The unsupported roof then caved in on itself. Scattered across the basalt are deep, jagged fissures. These cracks run parallel to the main rift valley. They are physical evidence of the tectonic stretching process. Some fissures are only a few centimeters wide. Others gape open entirely like bottomless dark canyons. A thin layer of pale sediment dusts the older rocks. This sediment provides a stark contrast to the black basalt. The newer lava flows remain completely bare and dark. The topography of the Rift Valley is highly complex. Steep fault scarps rise up on either side of us. These vertical cliffs were created by massive crustal blocks dropping. The walls of the valley look like giant rocky staircases. Each step represents a significant earthquake from the past. Despite the violent geology, the current mood is deeply peaceful. The dark water is exceptionally still and completely silent. There are no strong ocean currents in this sheltered valley. It feels like an ancient, undisturbed tomb of stone. Yet, this quiet landscape hides a spectacular secret. In 1977, scientists brought cameras to this exact spot. Researchers John Corliss and Robert Ballard led the historic expedition. They were towing a camera sled called the Angus. They expected to photograph a barren, lifeless volcanic desert. Instead, their temperature sensors detected a sudden thermal anomaly. The deep ocean water was inexplicably warm in specific patches. When they developed the film, they saw something impossible. Thriving communities of unknown animals clustered around rocky vents. It was a paradigm-shifting moment for marine biology. We are now tracing the very path of that expedition. Our submersible glides slowly over the undulating basalt terrain. Let us observe the subtle details of the ocean floor. The glassy basalt absorbs most of our artificial light. Shadows stretch long and dark behind every rocky mound. The water clarity is absolutely pristine at this depth. There is very little suspended matter to obscure our vision. We can see clearly for dozens of meters ahead. Every crack and crevice in the rock is sharply defined. We notice small pieces of white debris scattered about. These are the discarded shells of ancient marine organisms. They slowly dissolve in a high-pressure, cold water environment. The stark contrast of white on black is visually striking. As we move forward, the terrain becomes more fractured. We are approaching the most active central spreading axis. The density of tectonic fissures increases dramatically here. The ocean crust is literally tearing itself apart. This fracturing allows cold seawater to seep deep underground. The water travels down through miles of porous volcanic rock. It gets dangerously close to the underlying magma chamber. This subterranean journey fundamentally changes the water's chemistry. The extreme heat strips naturally occurring minerals from the surrounding rock. The superheated fluid becomes buoyant and rushes back upward. It escapes through the seafloor, creating the hydrothermal vents. We will soon encounter these magnificent underwater geysers. For now, we simply drift over the cooling lava fields. Take a deep breath and feel the profound tranquility. The immense weight of the ocean acts like a heavy blanket. It insulates us from the noise of the surface world. There are no storms or changing seasons down here. Time seems to stand completely still in the dark. The Galapagos Rift has existed for millions of years. It will continue to shape the Earth long after we leave. We are merely brief visitors in this ancient geological domain. The slow creation of new Earth is a mesmerizing process. Observe the gentle curves of the pillow lavas below. They look almost soft, despite being made of solid rock. The shapes mimic the rolling clouds of a gentle storm. Some mounds overlap perfectly, creating intricate natural sculptures. Nature's artwork remains hidden in the pitch-black ocean depths. We sweep our lights from left to right across the void. The beam catches a highly reflective surface in the distance. It is a massive wall of freshly exposed obsidian glass. This cliff face was likely sheared by a recent fault movement. The smooth black glass shines like a polished dark mirror. We carefully maneuver our vehicle closer to the sheer cliff. The thrusters purr softly, maintaining our delicate neutral buoyancy. Looking closely at the glass, we see microscopic striations. These tiny lines record the exact direction of the fault slip. Geologists can read these marks like an ancient history book. Every feature here tells a story of planetary mechanics. The Earth is a dynamic, living machine of rock and heat. The Galapagos Rift is one of its primary cooling valves. Without these spreading centers, the planet would overheat internally. The release of thermal energy is a slow, steady exhalation. It is the steady breathing of our home planet. We can almost feel the deep, rhythmic pulse of the Earth. Let the profound silence of the deep sea calm your mind. Imagine the 2.5 kilometers of water above you. It is a protective shield against the chaos of the surface. The crushing pressure outside holds everything in a firm embrace. Inside our cabin, the air is warm and easily breathable. The soft glow of the instrument panels illuminates our faces. Dials and gauges provide a continuous stream of reassuring data. The cabin oxygen levels remain perfectly stable and balanced. The carbon dioxide scrubbers hum quietly in the background. We are entirely self-sufficient in this hostile alien environment. We continue our slow flight along the valley floor. The terrain begins to slope gently upward ahead of us. We are climbing the flanks of a small volcanic shield. These low-profile volcanoes form frequently within the Rift Valley. They are built by repeated eruptions of highly fluid lava. The slope is incredibly smooth and easy to navigate. Our altitude sonar pings steadily as we follow the contour. A thin dusting of white biological material covers the slope. This indicates we might be nearing a hydrothermal source. The water temperature gauge shows a microscopic upward tick. It has risen from 2.0 to 2.1 degrees. This tiny shift is highly significant in the deep ocean. It confirms the presence of geothermal activity nearby. We pause our forward motion to assess the current environment. The submersible hovers motionlessly above the dark volcanic shield. We dim our exterior lights to absolute minimum power. The darkness of the abyss rushes back in instantly. It is a heavy, absolute blackness that feels almost tangible. Human eyes can detect no photons in this deep void. Yet, this lightless world is far from being dead. Chemical energy replaces solar energy in this unique ecosystem. The rocks beneath us hold the key to deep-sea survival. We restore the lights, pushing the comforting darkness away. The basalt floor reappears, solid and reassuring beneath us. Our journey along the Galapagos Rift has only just begun. We have successfully reached the ocean floor safely. We have navigated the complex tectonic plate boundary terrain. The immense pressure and freezing temperatures are fully documented. We now understand the geological forces shaping this dark valley. The stage is perfectly set for our upcoming biological discoveries. In the next phase, we will follow the thermal gradient. We will locate the towering chimneys of the active vents. But for now, rest in the quiet stability of the deep. Let the slow, steady rhythm of the ocean soothe you. The deep sea is a place of profound and endless peace. The year 1977 changed oceanographic science forever. Marine researchers sought the missing heat of the Earth. Plate tectonics was a newly accepted global scientific theory. Mid-ocean ridges produced vast amounts of thermal energy. Mathematical calculations showed a massive deficit in heat flow. Something was cooling the fresh oceanic crust very rapidly. Geologists suspected cold seawater was entering the fractured rock. This trapped water would heat up and rise outward. No human had ever seen such a submarine spring. The Galapagos Rift became the primary target for exploration. This active spreading center sits quietly near the equator. It slowly separates the Cocos Plate from the Nazca Plate. The dark Rift Valley lies 2,500 meters deep. Crucial clues emerged during a prior survey in 1976. The research vessel Melville sailed over the spreading ridge zone. Scientists deployed a deep tow instrument package in this area. This mechanical device trailed closely near the dark ocean floor. It carried sensitive thermistors to measure the ambient water temperature. The electronic sensors detected tiny thermal anomalies in the deep. Bottom water temperatures spiked by tiny fractions of a degree. Geochemists also collected deep water samples from this exact region. Laboratory analysis revealed highly elevated levels of helium-3 gas. This rare elemental isotope originates deep within the Earth mantle. Its presence strongly suggested active hydrothermal circulation occurring below. These subtle chemical hints paved the way for a return. A major scientific expedition was planned for the following year. Multiple research institutions collaborated on this ambitious scientific voyage. Woods Hole Oceanographic Institution provided essential technical marine resources. Scripps Institution of Oceanography sent their top geological experts. Oregon State University contributed brilliant specialists in marine chemistry. The National Science Foundation generously funded the entire complex endeavor. Chief scientists included Richard von Hazen and explorer Robert Ballard. Jack Corliss and John Edmund joined the expedition leadership team. Tjeerd van Andel brought decades of invaluable deep-sea geological experience. The research team consisted entirely of geologists and marine chemists. No biological scientists were invited on this specific research cruise. They only expected to find warm water and barren rocks. Biological life was considered impossible in such a toxic environment. Two distinct research vessels formed the specialized surface fleet. The ship Nor served as the primary scientific command center. It carried advanced acoustic mapping equipment and heavy towing winches. The smaller Lulu acted as the dedicated submarine mothership. This unusual catamaran was built from surplus military pontoon hulls. It provided a mobile launch platform for the manned submersible. Deep submergence vehicle Alvin rested securely on its central elevator. Alvin was a true marvel of modern deep-sea engineering. Its personnel sphere was forged from extremely thick titanium metal. This sphere protected 3 occupants from crushing abyssal water pressure. The pressure outside would reach over 250 atmospheres. Alvin could dive down to 4,000 meters perfectly safely. Before Alvin could dive, the team needed precise navigation targets. They utilized a specialized camera sled affectionately called the Angus. This acronym stood for Acoustically Navigated Geological Underwater Survey System. Angus was a heavy steel frame packed with monitoring instruments. It carried powerful strobe lights and color photographic film cameras. Sensitive temperature probes extended from its sturdy protective metal base. A long armored steel cable connected Angus to the Nor. Winch operators lowered the heavy metal sled into the abyss. They towed it just meters above the jagged volcanic rocks. Acoustic transponders on the seafloor provided exact spatial positioning data. This acoustic network allowed the Nor to track the sled accurately. The active search began in early February 1977. The ships arrived at 0 degrees 48 minutes north. The longitudinal coordinate was 86 degrees 9 minutes west. Graduate student Kathleen Crane monitored the telemetry at midnight exactly. She watched the continuous paper chart recorder very closely indeed. The mechanical pen traced a steady line of cold temperature. Deep ocean water usually hovers around 2 degrees Celsius here. Suddenly, the pen spiked sharply across the scrolling paper roll. The thermistor registered a significant rise in local water temperature. Crane quickly recorded the exact time and the acoustic coordinates. This distinct thermal anomaly lasted only a few brief moments. The sled had passed over something very unusual far below. Deck technicians hauled the heavy Angus sled back to the surface. They removed the waterproof camera housings from the steel frame. The 35mm color film required immediate chemical processing. Scientists gathered inside the cramped shipboard darkroom facility to watch. They anxiously examined the wet film against a bright light box. Most photographic frames showed barren landscapes of dark pillow lava. Then, a truly startling image appeared on the plastic strip. Hundreds of large white shapes littered the dark basaltic rocks. They were clearly the shells of massive deep-sea bivalve clams. Finding dense clusters of living clams here made absolutely no sense. The deep-sea floor is usually a barren biological desert. Nutritional food is exceptionally scarce at 2,500 meters. The first manned descent occurred on February 17 that year. Pilot Dudley Foster prepared the Alvin submersible for its launch. Jack Corliss and Tjeerd van Andel climbed into the titanium sphere. The heavy metal hatch was sealed tightly shut from the outside. Lulu lowered the white submarine into the calm Pacific Ocean. Alvin slipped beneath the blue waves and began its descent. Surface light faded quickly as they sank through the water column. Within 15 minutes, absolute darkness enveloped the tiny spherical vessel. The water temperature outside dropped to near freezing winter levels. Cold condensation formed slowly on the curved inner titanium walls. The dark journey to the bottom took over 90 minutes. Acoustic sonar pings measured their remaining distance to the rocky floor. Alvin switched on its powerful exterior lights near the bottom. The pilot established neutral buoyancy just above the oceanic crust. Fresh volcanic glass reflected the bright halogen bulb light beams. They navigated carefully toward the coordinates of the thermal spike. The submarine glided slowly over jagged ridges of hardened lava. Corliss stared intently through the small, thick acrylic viewing port. He looked desperately for any signs of the photographed clams. The external temperature sensor displayed exactly 2.0 degrees. Suddenly, the dark water ahead appeared to shimmer and dance. It looked exactly like heat rising from a hot summer highway. The digital temperature gauge began to climb upward very rapidly. The water temperature peaked at a surprising 17 degrees Celsius. This was shockingly warm for the deep abyssal ocean floor. Milky blue fluid seeped gently from the fractured volcanic rocks. Then, the true magnitude of the scientific discovery became clear. A vibrant oasis of strange life surrounded the warm springs. Giant white clams nestled tightly within the dark basalt crevices. Many of these bivalves measured over 30 centimeters in length. Blind white crabs scurried rapidly across the dark volcanic glass. Brown mussels clung to the jagged rocks in dense clusters. Pale pink fish swam lazily through the warm, shimmering water. The geologists were completely stunned by the incredible biological abundance. They had discovered an impossible living ecosystem in the dark. Corliss keyed the acoustic underwater telephone to contact the surface. His excited voice traveled upward through miles of cold water. He described the dense colonies of enormous living clam shells. The listening scientists aboard the Nor thought he was joking. They reminded him that they were a strict geological expedition. Corliss insisted that the thriving biological community was entirely real. He described the shimmering vent water and the strange animals. The surface team hastily consulted their onboard scientific reference library. They found absolutely nothing describing such a deep-sea ecosystem. This specific hydrothermal vent site was immediately dubbed Clam Bake. It became the first hydrothermal vent ever directly observed underwater. The submersible used its mechanical robotic arms to collect samples. Titanium syringes drew in the warm, shimmering mineral vent fluid. The water smelled strongly of rotten eggs upon its surface retrieval. High concentrations of dissolved hydrogen sulfide saturated the fluid samples. This highly toxic chemical would instantly kill most surface marine life. The team also collected various biological specimens for later laboratory study. They preserved the strange giant tube worms in a formaldehyde solution. Geochemist John Edmund analyzed the complex water chemistry on board. He found absolutely zero dissolved oxygen in the warm vent fluids. Instead, the water contained abundant dissolved mineral particles and heavy gases. This unique chemical signature held the key to the entire ecosystem. Scientists had to explain how these massive deep-sea animals survived. Sunlight cannot penetrate 2,500 meters of dense ocean water. Photosynthesis is completely impossible in this pitch-black abyssal marine realm. Microbiologist Holger Janusz later proposed a groundbreaking new biological theory. He suggested microscopic bacteria were oxidizing the toxic hydrogen sulfide gas. This chemical reaction released vital energy to build complex organic molecules. The biological process was named chemosynthesis instead of traditional solar photosynthesis. These highly specialized bacteria formed the base of the entire food web. Some bacteria lived freely floating in the warm hydrothermal vent water. Others lived symbiotically inside the soft tissues of the giant tube worms. This elegant symbiosis explained why the worms needed no digestive system. This monumental discovery fundamentally altered our modern understanding of biology. It proved definitively that life could thrive completely independently of the sun. Geothermal energy could sustain complex biological ecosystems in absolute total darkness. Textbooks on marine biology and oceanography had to be completely rewritten. The findings challenged long-held scientific assumptions about early life origins. Some scientists theorized early life began at similar ancient hydrothermal vents. The harsh chemical conditions resembled the chaotic early oceans of Earth. The 1977 expedition was a monumental triumph for science. It merged geology, chemistry, and biology into one cohesive new discipline. The deep ocean was clearly no longer a barren, empty wasteland. It was a dynamic environment hiding extraordinary biological and geological secrets. The Galapagos Rift marks a deep tectonic boundary. Two massive crustal plates separate in this dark abyss. The Cocos Plate drifts slowly toward the northern horizon. Meanwhile, the Nazca Plate moves steadily to the south. This divergent boundary stretches across the eastern Pacific Ocean. Deep below the surface, molten rock drives this separation. The Rift Valley floor sits at 2,500 meters deep. Immense hydrostatic pressure blankets the newly formed basaltic crust. Geologists classify this region as an intermediate spreading center. The tectonic plates move about 50 millimeters every year. This specific spreading rate dictates the local geological topography. Fresh magma rises from the upper mantle continuously here. It collects in shallow chambers beneath the ocean floor. The molten rock eventually breaches the thin crustal layer. Submarine eruptions occur in absolute darkness and freezing temperatures. Lava extrudes slowly into the near-freezing deep ocean water. The outer surface of the lava cools almost instantly. This rapid quenching forms distinct bulbous shapes called pillows. Pillow basalts dominate the central axis of the rift. Their glassy rinds reflect the lights of deep submersibles. Inside these pillows, the liquid rock cools much slower. This varied cooling rate creates unique crystalline structures inside. Not all eruptions at the rift produce pillow lavas. Higher eruption rates create vast, flat sheet flows instead. These sheet flows spread rapidly across the Rift Valley. They pave the ocean floor with smooth, glassy basalt. Sometimes, the lava drains away beneath the solidifying crust. This process leaves behind hollow, fragile basaltic lava pillars. Submersibles must navigate these delicate structures with extreme care. The tall pillars show horizontal marks from receding lava. In 1977, the research vessel Noor sailed these waters. Scientists aboard sought to understand this exact geological process. Robert Ballard led the deep camera sled named Angus. Angus captured the first images of these fresh lavas. Jack Corliss later descended in the submersible named Alvin. Alvin hovered above the jagged basaltic sea floor below. The crew observed deep fissures cutting through the rock. These axial fissures run parallel to the spreading center. Tectonic tension pulls the young crust apart constantly here. Deep cracks propagate downward into the warm rock layers. The Rift Valley floor contains hundreds of parallel fissures. Some structural cracks measure merely a few centimeters wide. Others gape open to widths of several meters across. These open chasms drop deep into the dark crust. They provide direct conduits for the descending cold seawater. Cold seawater sinks deep into these open tectonic fractures. The ambient water temperature hovers around 2 degrees Celsius. Gravity pulls the dense water deep into the crust. It descends thousands of meters through the porous basalt. The water approaches the underlying hot magma chamber eventually. Geothermal heat warms the descending fluid to extreme temperatures. The water reaches temperatures exceeding 300 degrees Celsius. High deep-sea pressure prevents this superheated fluid from boiling. A complex chemical exchange begins deep within the crust. The heated water reacts violently with the surrounding basalt. Sulfate molecules in the seawater drop out of solution. The subterranean fluid becomes highly acidic as it heats. This hot, acidic water acts as a powerful solvent. It leaches heavy metals directly from the surrounding rocks. Iron dissolves easily into the superheated deep subterranean fluid. Copper and zinc follow suit in very large quantities. Manganese and silica also join the ascending chemical mixture. The fluid absorbs hydrogen sulfide from the volcanic rock. Now laden with minerals, the fluid becomes highly buoyant. It rushes upward through narrow channels in the crust. The upward journey to the seafloor takes several hours. The mineral-rich fluid finally erupts from the ocean floor. It meets the freezing, oxygen-rich water of the abyss. A sudden and dramatic chemical precipitation occurs immediately here. Dissolved minerals solidify instantly upon hitting the cold water. Anhydrite forms the initial foundation of the vent structures. This calcium sulfate mineral creates a delicate porous matrix. Chalcopyrite precipitates next, adding copper to the growing walls. Sphalerite contributes distinct dark bands of zinc to chimneys. Iron sulfide particles billow outward like thick dark smoke. This off-axis rock might be 100,000 years old. Beneath the basalt layer lies a thick zone of gabbro. Gabbro forms when magma cools very slowly deep underground. Its large mineral crystals indicate a gradual cooling process. Further down lies the Mohorovicic discontinuity, or the Moho. This boundary separates the oceanic crust from the mantle. Below the Moho rests dense rock known as peridotite. Peridotite consists mostly of the green mineral called olivine. The Galapagos Rift exposes some of these deeper rocks. Transform faults offset the spreading center in several places. These deep faults slice through the crust at sharp angles. They reveal the internal stratigraphy of the ocean floor. Scientists map these deep layers using advanced sonar techniques. A deep mantle plume sits near the spreading center. This Galapagos hotspot influences the local rift geology heavily. It provides a massive influx of excess thermal energy. The hotspot creates a shallower bathymetry along the rift. The ocean floor rises gently toward the nearby archipelago. Chemical signatures of the hotspot appear in the basalt. Isotope analysis reveals a mixture of different mantle sources. Researchers study these isotopes to trace the magma's origin. The interaction between hotspot and rift remains highly complex. It creates a unique geochemical environment found nowhere else. The primary vent field sits at 0 degrees latitude. Its longitude is 86 degrees west in the Pacific. The submersible Alvin recorded fluid temperatures here in 1977. Thermometers registered 17 degrees Celsius at the Rose Garden. This was much warmer than the surrounding deep water. Later expeditions found much hotter vents along the rift. Some deep vents release fluids exceeding 350 degrees. He dropped long thermal probes into the ocean floor. The probes penetrated the thin sediment near the rift. They recorded massive heat radiating from the young crust. These measurements confirmed the presence of deep hydrothermal circulation. The heat loss matched mathematical models of plate tectonics. Scientists mapped the Rift Valley using multibeam sonar arrays. The sonar revealed a central graben structure in the crust. Steep fault scarps form the walls of this deep valley. The valley walls rise hundreds of meters above the floor. Terraces of older basalt step up toward the abyssal plain. Each terrace represents a past phase of volcanic spreading. The geology here acts as a physical recording device. It captures the history of the Earth's magnetic field. As basalt cools, iron minerals align with magnetic north. The rock solidifies, locking this magnetic orientation firmly in place. Hydrothermal mounds slowly oxidize in the cold deep ocean. Their bright metallic colors fade to a dull rust. New chimneys often sprout directly from these ancient mounds. The underlying fluid pathways remain active for many decades. Eventually, tectonic movement shifts the crust away from the heat. The magma chamber no longer warms the descending seawater. The hydrothermal circulation slows down and finally stops completely. The towering vent structures become cold and completely dormant. Slowly, marine sediments bury the extinct sulfide mineral deposits. In recent years, remotely operated vehicles explored the rift. The ROV Hercules mapped the vent fields with high precision. High-definition cameras revealed the intricate textures of the chimneys. Laser scanners created exact three-dimensional models of the seafloor. These models help scientists track geological changes over time. Researchers observed how tectonic strains alter the vent pathways. Deep within the Galapagos Rift, mineral structures rise from the seafloor. These towering formations are known as hydrothermal vent chimneys. They create a jagged landscape in total oceanic darkness. The submersible Alvin first illuminated these geological wonders. Scientists like Jack Corliss observed them through thick acrylic viewports. Superheated fluids continuously erupt from the rocky ocean crust. The water escapes at searing temperatures approaching 400 degrees Celsius. Extreme hydrostatic pressure prevents this boiling liquid from vaporizing. The depth here measures exactly 2,500 meters. Two distinct types of chimneys dominate this hydrothermal environment. Researchers classify them simply as black smokers and white smokers. Black smokers represent the hottest vents in the Galapagos Rift. Their internal fluid temperatures frequently range from 350 to 400 degrees. These dark plumes consist of fine-grained metallic sulfide minerals. Iron and copper compounds give the emissions their characteristic black color. The hot vent fluid is highly acidic with a low pH. It carries dissolved metals from deep within the Earth's crust. Magma chambers located kilometers below provide the necessary thermal energy. Cold seawater seeps down into cracks along the tectonic spreading center. This water reacts chemically with the hot basaltic rocks. Magnesium and sulfate are entirely removed during this subterranean journey. The fluid becomes enriched with heavy metals and hydrogen sulfide. Buoyancy forces drive this altered, superheated liquid back upward. It eventually exits the seafloor through narrow mineralized conduits. Upon reaching the ocean floor, the hot fluid meets freezing seawater. Deep ocean water maintains a constant temperature of 2 degrees Celsius. This drastic temperature gradient causes immediate chemical precipitation. Dissolved minerals instantly solidify into tiny particulate matter. These particles fall and accumulate around the vent opening. A porous mineral ring begins to form on the basalt floor. Calcium sulfate, known as anhydrite, is the first mineral to precipitate. Anhydrite creates a fragile framework for the developing chimney structure. The chimney walls grow taller as more fluid escapes and cools. Copper iron sulfide, or chalcopyrite, lines the inner walls. This interior lining directly contacts the hottest flowing liquids. Zinc sulfide precipitates within the cooler outer layers of the wall. These mineral spires can reach astonishing heights over time. Some Galapagos Rift chimneys stand over 20 meters tall. A few exceptional structures grow up to 50 meters high. They resemble Gothic cathedrals constructed entirely of dark metallic ores. The growth rate of a black smoker is remarkably fast. Active chimneys can grow up to 30 centimeters in a single day. This rapid accumulation makes them highly unstable geological features. Tall chimneys frequently collapse under their own massive weight. Tectonic tremors along the rift zone also trigger structural failures. When a spire falls, the hydrothermal fluid simply finds another exit. A new chimney immediately begins forming on the fresh mineral rubble. The seafloor here is littered with massive fallen sulfide blocks. White smokers present a stark contrast to their darker counterparts. These vents emit lighter-colored plumes of mineral-rich water. Their fluid temperatures are significantly cooler than black smokers. White smoker emissions typically range from 250 to 300 degrees Celsius. The lighter color comes from different precipitated chemical compounds. Barium, calcium, and silicon dominate the white smoker plumes. Barium sulfate and silica give the water a milky appearance. These vents often form on the periphery of the main hydrothermal field. The fluid travels further through the crust before venting. This extended journey cools the liquid before it reaches the surface. Subsurface mixing with cold seawater also lowers the exit temperature. White smoker chimneys lack the dark iron sulfides of black smokers. Their structures are generally smaller and more delicately formed. Scientists must use specialized equipment to study these extreme environments. The submersible Alvin employs precise robotic arms for sample collection. Titanium syringes are used to draw the superheated vent fluids. Standard materials would instantly melt or dissolve in the corrosive flow. Robert Ballard directed many of these early sampling missions. The research vessel Nor supported Alvin from the ocean surface. Precise temperature probes were inserted directly into the chimney orifices. The first readings melted the plastic casings of the instruments. Engineers had to design new probes coated in heat-resistant ceramics. These advanced sensors finally recorded the true 400-degree temperatures. The chemical analysis of the fluid revealed astonishing concentrations. Hydrogen sulfide levels were millions of times higher than normal seawater. The interior of a black smoker chimney is incredibly complex. Fluid dynamics dictate the continuous remodeling of the inner channels. The central conduit remains open due to the high flow velocity. Slower moving fluids near the edges allow minerals to crystallize. This process thickens the chimney walls from the inside out. The outer surface of the spire is highly porous and sponge-like. Cold seawater constantly permeates through these outer mineral layers. It meets the outward diffusing hot fluids within the wall matrix. This creates a steep thermal gradient across a few centimeters. The temperature drops from nearly 400 degrees to just 2. Such extreme gradients foster diverse zones of mineral deposition. Pyrite, known as fool's gold, glints within the fractured rock. The Galapagos Rift contains several distinct hydrothermal vent fields. The Rose Garden field became famous for its vibrant structures. Its precise coordinates are 0 degrees 48 minutes north latitude. The longitude marks 86 degrees 13 minutes west. Here, the mineral chimneys are surrounded by extensive basalt flows. Pillow lavas form bulbous shapes beneath the towering sulfide spires. Sheet flows create flat, glassy surfaces reflecting the submersible's lights. The chimneys rise from fissures in this recently solidified crust. Kathleen Crane helped map these geological features using towed cameras. Her thermal anomaly maps guided Alvin directly to the active vents. Another nearby field is aptly named the Rosebud Vent Site. Rosebud features younger, smaller chimneys just beginning their growth cycle. The dark smoke from the vents is not actually smoke. It is a dense cloud of suspended polymetallic sulfide particulates. As the plume rises, it slowly dilutes into the surrounding ocean. Ocean currents carry these mineral particles for thousands of kilometers. They eventually settle to form metalliferous sediment on the seafloor. These sediments provide a historical record of past hydrothermal activity. The vent fluids also contain significant amounts of dissolved gases. Carbon dioxide and methane bubble upward in the superheated stream. Helium-3, a rare isotope, is a crucial tracer for vent fluids. Its presence confirms the fluid's origin deep within the Earth's mantle. Scientists use mass spectrometers to measure these volatile chemical signatures. The chemical energy released here rivals the power of sunlight. The texture of a hydrothermal chimney varies along its height. The base is massive, solid, and heavily oxidized by seawater. Rust-colored iron oxides coat the lower sections of the spire. Higher up, the structure becomes more fragile and intricately branched. Multiple smaller spouts often diverge from the main central trunk. These secondary vents create a candelabra effect in the darkness. Flange structures sometimes form horizontal ledges on the chimney sides. Hot fluid pools beneath these overhanging flanges before spilling upward. The underside of a flange acts as a mirror for acoustic waves. Remotely operated vehicles navigate carefully around these delicate horizontal extensions. A single bump from a robotic arm can shatter the formations. The broken pieces slowly dissolve back into the cold deep ocean. Hydrothermal chimneys have relatively short lifespans in geological terms. A single vent might remain active for only a few decades. Mineral precipitation eventually clogs the subsurface plumbing system. The flow of superheated fluid gradually slows and stops completely. Without the hot fluid, the chimney begins to decay immediately. Cold seawater penetrates the structure and oxidizes the sulfide minerals. The towering spire slowly crumbles into a mound of metallic rust. These inactive sulfide mounds dot the landscape of the Galapagos Rift. They mark the locations of ancient, extinct hydrothermal vent fields. Geologists study these fossilized chimneys to understand oceanic crust evolution. Core samples drilled from the mounds reveal layers of past activity. Magma shifting beneath the rift zone dictates this continuous cycle. The Galapagos Rift is part of the global mid-ocean ridge system. It forms a diverging boundary between the Cocos and Nazca plates. As these tectonic plates pull apart, deep fissures open constantly. This constant fracturing provides new pathways for seawater to enter. The geological activity here is relatively slow compared to other ridges. The spreading rate is approximately 50 mm per year. This intermediate spreading rate influences the spacing of the vent fields. Black smokers here are less densely packed than on fast-spreading ridges. The structural integrity of the crust allows deeper fluid circulation. Deep circulation produces highly concentrated, incredibly hot hydrothermal emissions. The resulting chimneys represent a pure extraction of mantle elements. Woods Hole Oceanographic Institution continues to analyze the Galapagos structures. Advanced sonar mapping reveals the exact distribution of the chimneys. Autonomous underwater vehicles glide silently above the jagged mineral canopy. They record high-resolution bathymetric data of the Rift Valley floor. The maps show distinct clusters of chimneys aligned along fault lines. These fault zones dictate the precise location of every black smoker. Acoustic Doppler current profilers measure the velocity of the rising plumes. The vent fluid shoots upward at speeds exceeding 1 meter per second. This rapid ejection creates turbulent eddies in the surrounding water column. The turbulence helps mix the chemical nutrients into the deep ocean. Manganese anomalies in the water column first hinted at these structures. The physical presence of a black smoker alters local ocean currents. The massive heat flux generates powerful upward convection columns. These thermal updrafts draw cold bottom water toward the vent field. The continuous inflow creates a gentle breeze across the ocean floor. Suspended particles drift slowly toward the base of the active chimneys. The temperature of the rock surface varies wildly within millimeters. A probe touching the chimney exterior registers 2 degrees Celsius. Pushing the probe 1 centimeter deeper reveals a 100-degree increase. The mineral walls act as incredibly efficient thermal insulators. This insulation keeps the inner core fluid at maximum temperature. Without this mineral barrier, the fluid would cool instantly upon exiting. The chimney essentially functions as a pressurized geological exhaust pipe. The discovery of these structures completely transformed modern marine geology. Before the famous Galapagos Rift expedition, the deep seafloor seemed entirely barren. The towering black and white smokers proved the ocean crust is dynamic. They demonstrated how oceans chemically interact with the Earth's interior. Every chimney acts as a vital chemical refinery for the sea. The constant venting regulates the chemical balance of the global ocean. Magnesium is continuously extracted from the sea by these systems. Calcium and potassium are simultaneously added to the ocean waters. The physical structures of the Galapagos Rift are silent, towering monuments. They stand as testaments to the immense power of geothermal energy. Hidden in darkness, these chimneys continue their ancient cycle of creation. We descend deeper into the dark waters of the Galapagos Rift. The ambient ocean here is cold, still, and relatively uniform. Normal deep seawater maintains a stable pH of around 8. It carries dissolved oxygen from the distant polar surface waters. But the environment shifts dramatically near the hydrothermal vent fissures. The submersible Alvin approaches a shimmering veil of warm fluid. Inside this tiny sphere, scientists monitor external chemical sensor readings. The water chemistry changes completely within just a few meters. Deep beneath the seafloor, ocean water permeates fractured basaltic crust. Magma chambers heat this trapped water to extreme underground temperatures. The fluid expands, becoming buoyant and highly reactive with rocks. Magnesium and sulfate are entirely stripped from the sinking seawater. This process makes the subterranean fluid highly acidic and corrosive. Geochemist John Edmund analyzed these early Galapagos water samples carefully. He discovered that the vent fluid pH drops significantly here. The readings show a highly acidic pH of about 3. This acidic liquid dissolves heavy metals from the surrounding basalt. Iron, manganese, and copper leach into the superheated water stream. The fluid eventually rushes back upward toward the ocean floor. It exits the crust at temperatures around 17 degrees Celsius. This was the temperature measured at the Rose Garden site. The fluid mixes instantly with the freezing ambient bottom water. This sudden mixing creates a unique chemical gradient for life. Hydrogen sulfide is the most crucial chemical component found here. Normal seawater contains virtually zero traces of this toxic gas. But the Galapagos vent fluids carry immense concentrations of it. Sensors record sulfide levels exceeding 3 millimoles per fluid liter. For most marine life, this concentration is completely lethal. Hydrogen sulfide binds to hemoglobin and halts cellular respiration processes. Yet specialized bacteria here use it as an energy source. They oxidize the sulfide to produce organic carbon in darkness. This chemical reaction forms the absolute base of the food web. The discovery of this process revolutionized modern biological oceanography completely. Jack Corliss realized the profound implications of these chemical readings. Sunlight was no longer required to sustain a biological community. The Earth itself provided the chemical fuel for these organisms. Methane is another significant molecule venting from the Galapagos fissures. Unlike surface methane, this gas forms through purely abiotic processes. Carbon dioxide reacts with hydrogen deep within the planetary crust. This reaction requires specific iron and nickel mineral catalysts underground. The process is known scientifically as the Sabatier reaction pathway. Methane concentrations here reach up to 50 micromoles per liter. Certain deep ocean microbes consume this methane to fuel their metabolism. They thrive in the warm transition zones around the vents. Salinity levels in the Galapagos fluids also present fascinating variations. Normal deep ocean water has a steady salinity of 35. Vent fluids can be significantly saltier or fresher than seawater. This variation depends on a phenomenon called subterranean phase separation. When seawater boils underground, it separates into vapor and brine. The dense brine sinks deeper into the fractured crustal rocks. The lighter vapor phase rises quickly toward the ocean floor. Galapagos vent fluids often show lower salinity than ambient seawater. This indicates the presence of condensed vapor in the discharge. Researchers measure chloride concentrations to track these subtle salinity shifts. The chemical signature of the Galapagos Rift is quite distinct. We can compare it to other famous hydrothermal vent fields. The East Pacific Rise sits further west in the ocean. Vents there eject fluid at 350 degrees Celsius. Those superheated fluids create massive, towering black smoker mineral chimneys. The East Pacific Rise fluids carry much higher metal concentrations. Iron and zinc precipitate immediately upon hitting the cold seawater. This creates the thick black smoke characteristic of those vents. In contrast, the Galapagos fluids are cooler and heavily diluted. Subsurface mixing cools the fluid before it reaches the seafloor. Much of the heavy metal content precipitates beneath the crust. The resulting Galapagos emissions are mostly clear and gently shimmering. The Mid-Atlantic Ridge offers another fascinating chemical contrast to consider. The Lost City hydrothermal field operates on entirely different chemistry. Lost City vents are highly alkaline, reaching a pH of 10. They are driven by the serpentinization of exposed mantle rock. The Galapagos Rift is driven by the cooling of basaltic magma. Its fluids remain strictly acidic until they mix with seawater. The Mariana Back Arc Basin presents yet another unique chemical environment. Vents there emit extremely high levels of dissolved carbon dioxide. The Galapagos fluids contain moderate dissolved inorganic carbon by comparison. Each vent field possesses a distinct chemical fingerprint and signature. The titanium pressure holovalve protects the scientists inside. Outside, the corrosive fluid silently bathed the submersible mechanical arms. Robert Ballard observed the milky blue water at the vents. The color comes from tiny particles of precipitated elemental sulfur. These sulfur particles form when hydrogen sulfide oxidizes in seawater. The water slowly turns cloudy as it drifts upward away. Specialized instruments draw water samples into sealed titanium syringe bottles. These bottles maintain the extreme pressure of the ocean depths. This prevents dissolved gases from escaping during the long ascent. Without this pressure, the samples would boil on the ship. Scientists analyze these samples in the laboratory aboard the Nor. They use gas chromatography to measure the exact methane levels. Titration reveals the precise concentration of dissolved hydrogen sulfide gas. The chemical data tells a story of underground geological alchemy. Water and rock interact under 250 atmospheres of pressure. The chemical equilibrium shifts constantly as temperature and pressure change. Dissolved silica is another key component of the vent fluid. Basaltic glass dissolves easily in the hot, acidic subterranean environment. Silica concentrations in the fluid reach 20 millimoles per liter. This is vastly higher than the surrounding deep ocean water. Oceanographers use silica levels to calculate the fluid maximum temperature. This chemical geothermometer reveals the hidden thermal history of water. The data suggests the water reached 300 degrees underground. It then cooled significantly as it rose through the crust. Potassium levels also change dramatically during the deep crustal circulation. The hot fluid extracts potassium from the surrounding volcanic rock. Galapagos vent samples show significant potassium enrichment compared to seawater. Conversely, magnesium is almost entirely absent from the emerging fluids. Magnesium precipitates out as clay minerals deep within the crust. This complete removal of magnesium is a hallmark of hydrothermal vents. It helps scientists confirm the purity of their fluid samples. Any magnesium found in a sample indicates mixing with ambient seawater. The chemical gradients sustain a massive biomass of specialized organisms. The Rift Valley floor sits at a depth of 2,500 meters. Here, the pressure keeps the superheated fluids from boiling instantly. The physical chemistry of water changes fundamentally at these depths. Its density and heat capacity respond to the immense pressure. The Galapagos fluids are relatively buoyant compared to surrounding water. They form a rising plume that drifts along the seafloor. Ocean currents slowly disperse these chemical signatures across the Pacific. The dissolved iron eventually oxidizes and falls as fine sediment. This creates a metalliferous layer on the surrounding ocean floor. Manganese disperses much further, creating a massive chemical halo underwater. This halo helps researchers locate undiscovered vent fields from afar. The chemical balance of the entire ocean is affected here. Hydrothermal vents act as a continuous chemical regulatory system globally. They remove certain elements from seawater while adding many others. This exchange balances the chemical input from terrestrial river systems. Before 1977, this crucial global chemical cycle remained unknown. The discovery at the Galapagos Rift solved a major oceanographic mystery. The chemical composition of the ocean is maintained by these vents. Helium isotopes provide another fascinating clue to the geological processes. The vent fluids contain high levels of the isotope helium-3. Helium-3 is a primordial gas trapped since the Earth formed. It leaks from the mantle into the ascending hydrothermal fluids. Normal seawater contains very little of this ancient, rare isotope. Scientists use helium-3 as a highly sensitive chemical tracer molecule. It allows them to track the vent plume for thousands of kilometers. The Galapagos plume spreads westward across the deep Pacific basin. The silent drift of these chemicals happens in complete darkness. The deep sea remains undisturbed by the storms far above. The chemical environment here is remarkably stable over human timescales. The continuous flow of hydrogen sulfide supports generations of microbes. The water temperature fluctuates only slightly near the vent openings. The ambient ocean remains at a constant 2 degrees Celsius. The mixing zone creates microhabitats with highly specific chemical conditions. Some bacteria prefer high sulfide and lower oxygen concentration levels. Others thrive where the fluid is cooler and highly diluted. This chemical stratification allows diverse microbial communities to coexist peacefully. The submersible external lights illuminate the gently shimmering water column. The visual distortion is caused by the mixing of different fluid densities. It looks like heat rising from a hot paved road. This phenomenon is known as the Schlieren effect in fluid dynamics. The cameras captured this subtle optical distortion for the researchers. The chemical sensors on Alvin continuously log the changing parameters. Conductivity, temperature, and depth are recorded every single passing second. The data stream paints a detailed picture of the invisible chemistry. Lithium is another trace element found enriched in these waters. It is leached from the basalt during the high-temperature reaction phase. The concentration of lithium helps determine the water-rock interaction ratio. The deep sea holds many chemical secrets waiting to be discovered. We will continue exploring these quiet depths in our future documentary journeys. The Galapagos Rift lies deep beneath the dark Pacific Ocean. Coordinates 0 degrees 48 minutes north mark this volcanic location. 86 degrees 5 minutes west pinpoints the exact map position. Here, the barren seafloor sits exactly 2,500 meters deep. Total darkness blankets this remote oceanic ridge environment for eternity. Yet, abundant life thrives in this eternal midnight abyssal zone. Vast microbial mats cover the dark basalt rocks like snow. These white bacterial sheets form the ultimate foundation of life. They rely entirely on toxic hydrogen sulfide from thermal vents. Chemosynthesis replaces photosynthesis in this sunless world completely and efficiently. Microbes convert chemical energy into usable organic carbon for growth. Filamentous bacteria called Beggiatoa dominate these thick white mat structures. Some microbial layers measure several centimeters thick across jagged rocks. They tolerate fluid temperatures reaching 35 degrees Celsius with ease. The surrounding deep seawater remains at a frigid 2 degrees. This extreme thermal gradient provides energy for rapid bacterial reproduction. Scientists aboard the submersible Alvin first observed these living mats. Geologist Jack Corliss noted the milky blue water during dives. The year 1977 changed modern marine biology paradigms forever. These tiny microbes support an incredibly dense community of creatures. The sheer biomass here rivals productive tropical rainforest ecosystems easily. Researchers measure biological biomass in kilograms per square meter here. Typical deep ocean floors host barely milligrams of living tissue. The Galapagos Rift vent fields shatter these normal ecological expectations. Life concentrates tightly around the warm hydrothermal fluid emissions flowing. Giant tube worms dominate the visual underwater landscape completely everywhere. Their formal scientific name is Riftia pachyptela in taxonomic records. These strange alien creatures lack both a mouth and stomach. They can grow up to 2.5 meters. White chitinous tubes protect their soft internal biological structures safely. Brilliant red biological plumes emerge from the tops of tubes. Complex hemoglobin fills these plumes to capture hydrogen sulfide efficiently. The giant worms absorb oxygen and toxic sulfide from water. They transport these captured chemicals to a specialized internal organ. This unique internal organ is called the trophisome by biologists. Billions of symbiotic bacteria live comfortably inside this dark tissue. The internal bacteria manufacture organic food directly for the host. Population densities of Riftia reach 200 individuals per meter. They grow incredibly rapidly in the warm nutrient-fluid currents. Some healthy individuals lengthen by 80 centimeters in 1 year. Giant white clams also populate the Galapagos Rift seafloor densely. Calyptargina magnifica is the precise scientific classification for these mollusks. Their heavy calcium shells measure up to 26 centimeters long. These massive clams wedge themselves deep into dark basalt crevices. They position their sensitive gills near the warm mineral flow. Like the tube worms, they rely heavily on symbiotic bacteria. Their cold blood runs red with specialized hemoglobin protein structures. Dense clam beds stretch for many meters along active fissures. Hundreds of large clams can pack tightly into 1 meter. They filter vital chemical nutrients directly from surrounding vent water. Bathymodialus thermophilus mussels share this crowded hydrothermal vent habitat peacefully. These brown mussels attach to bare rocks using strong threads. They form massive dense clusters near the giant clam beds. Mussel populations often exceed 1,000 individual animals per meter. Unlike tube worms, these mussels retain a functional digestive tract. They can filter feed on free bacteria during lean times. This dual feeding strategy ensures their survival in this habitat. The active vent fields host many highly unique endemic species. These specific strange creatures exist nowhere else on planet Earth. The famous Galapagos vent dandelion is a bizarre aquatic organism. Its scientific name is Thermophalia taraxacca in marine biological literature. This weird creature is actually a complex floating animal colony. It belongs to the Siphonophore family of fragile invertebrate species. The dandelion appears as a faintly glowing yellow sphere underwater. It anchors itself to smooth rocks using delicate stinging tentacles. These slow scavengers feed on small crustaceans and organic debris. They often signal the declining chemical phase of dying vents. Pale squat lobsters crawl slowly across the dense mussel beds. Munidopsis subsquamosa is the dominant crustacean species in this zone. These completely blind white crabs possess long and slender claws. They scavenge dead animal tissue from the thriving vent community. Their population density remains relatively low compared to packed mollusks. Researchers count perhaps 2 adult squat lobsters per square meter. Galapagos vent eelpouts swim languidly through the warm, shimmering water. Thermasis cerberus is a uniquely pale pink fish species here. They measure about 30 centimeters long from head to tail. These strange fish lack pelvic fins and move very sluggishly. They actively hunt small amphipods hiding among giant tube worms. The eelpouts tolerate high hydrogen sulfide concentrations without suffering harm. Their incredibly slow metabolism conserves precious biological energy in darkness. Oceanographer Robert Ballard documented these intricate food webs during dives. The submersible Alvin captured thousands of detailed photographs for analysis. Biologists carefully mapped the precise spatial distribution of every species. Water temperature dictates the exact physical location of each group. Tube worms occupy the hottest water zones directly above vents. They bathe in flowing fluids reaching 20 degrees Celsius constantly. Giant clams prefer slightly cooler ambient water at 10 degrees. Mussels thrive in mixed fluids measuring just 5 degrees nearby. Crustacean scavengers roam the cold dark periphery at 2 degrees. This strict thermal zonation creates distinct concentric rings of life. The entire thriving ecosystem extends outward for only few meters. Beyond this chemical oasis, the barren abyssal plain resumes dominance. The ecological contrast between vent and plain is incredibly stark. Total biomass drops by a factor of 10,000 immediately. Chemical nutrient availability dictates this sharp biological boundary line clearly. Small aquatic limpets graze directly on the thick microbial mats. These tiny snails scrape nutritious bacteria from hard basalt surfaces. Their microscopic velar teeth are reinforced with hard iron minerals. Thousands of these limpets can easily cover a single meter. They convert bacterial mat biomass into accessible food for predators. Large vent crabs forcefully tear pieces of flesh from clams. Bythagria thermodron is the undisputed top crustacean predator found here. These aggressive crabs lack functional visual eyes in adult stages. They rely entirely on sensitive chemical sensors to locate prey. Their smooth white carapaces blend perfectly with pale clam shells. Crab population densities reach 10 individual animals per square meter. They can easily survive extreme hydrostatic pressure at crushing depths. 250 atmospheric units compress their small armored bodies. Specialized cellular proteins prevent their internal biological structures from collapsing. Small polychaete worms construct delicate protective tubes on bare rock. Alvinellid worms prefer the absolute hottest fluid flows available below. They can withstand scalding temperatures near 40 degrees Celsius easily. Their soft bodies are covered in a thick bacterial fleece. These episymbiotic bacteria actively detoxify dangerous heavy metals from water. The worms secrete sticky mucus to feed their protective microbes. This brilliant mutualistic relationship ensures mutual survival in toxic zones. Serpulid worms filter small particles using delicate red biological crowns. They retract incredibly quickly when a blind predatory crab approaches. Tiny amphipods swarm thickly in the warm water column above. These small crustaceans resemble frantically swimming fleas in submersible lights. Ventiella sulphuris is a highly abundant amphipod species in regions. They form massive dense swarms of thousands of swimming individuals. Their combined biomass contributes significantly to the local food web. Pale anemones attach securely to peripheral rocks in cooler waters. They capture drifting organic matter with their long stinging tentacles. These simple cnidarians completely lack the symbiotic bacteria of worms. They rely entirely on the biological fallout from active vents. Octopuses occasionally visit the Galapagos Rift from surrounding endless darkness. Vulcanoctopus hydrothermalis is a very small benthic cephalopod species here. They silently hunt crabs among the dense white tube worms. These ghostly octopuses have absolutely no ink sacs inside them. Defensive ink is completely useless in environments with no sunlight. Their pale skin lacks the complex color chromatophores of octopuses. Their visual eyes are reduced but can detect faint glows. Hydrothermal vents emit a faint infrared light called crystalloluminescence constantly. Some deep predators might actually use this dim glow daily. The microbial mats also release very weak chemical light signatures. Swarming shrimp species are surprisingly absent from the Galapagos Rift. Atlantic Ocean vents host massive chaotic swarms of blind shrimp. The Pacific Galapagos fields remain peacefully dominated by giant worms. Remotely operated vehicles have mapped this entire area very extensively. The ROV Jason captured stunning high-resolution video of communities. Vent fields are highly ephemeral habitats with short geological lifespans. A typical Galapagos vent might remain biologically active for decades. Eventually, the subterranean volcanic plumbing shifts due to tectonic forces. The steady flow of warm mineral water stops very suddenly. When the fluid ceases, the foundational white microbial mats die. The giant tube worms starve quickly without internal symbiotic bacteria. Scavengers consume the decaying biological remains of the oasis ecosystem. Soon, only empty white clam shells litter the dead basalt. However, new thermal vents open constantly along the Rift Valley. Microscopic larvae drift through the cold water seeking new vents. Riftsha larvae can survive for many weeks in open water. They ride deep ocean currents along the active volcanic ridge. Chemical sensors guide them toward fresh hydrogen sulfide fluid plumes. Upon finding a new vent, they settle on bare rocks. The microscopic larvae transform into juvenile tube worms very rapidly. They acquire their essential symbiotic bacteria from the surrounding environment. A brand new biological community establishes itself within 1 year. This endless cycle of destruction and rebirth defines the Rift. The Rose Garden was a legendary Galapagos hydrothermal vent site. Researchers discovered it in 1979 during an ocean expedition. It featured spectacular dense clusters of red tube worms everywhere. Scientists returned to the famous Rose Garden in 2000. Fresh molten lava flows had completely paved over the site. The beautiful biological community was buried beneath solid black rock. Yet, a new site called Rosebud had already formed nearby. Juvenile tube worms were already colonizing the fresh cooling lava. Life here proves incredibly resilient despite the harsh volcanic conditions. Deep ocean currents carry genetic material across vast distances constantly. Gene flow between different vent fields maintains healthy biological diversity. Marine geneticists analyze the complex DNA of these unique organisms. They discover fascinating adaptations to extreme pressure and toxic chemicals. The enzymes of vent bacteria function perfectly at high temperatures. Industrial scientists study these heat-resistant enzymes for medical applications. The Galapagos Rift ecosystem remains a crucial laboratory for biology. It shows how life adapts to environments completely lacking sunlight. The discoveries at the Galapagos Rift expanded our scientific horizons. Before 1977, all known ecosystems relied on solar energy. This dark abyss proved that chemical energy sustains complex communities. The Galapagos Rift ecosystem exists in absolute darkness. This unique biological community completely altered marine biology. Scientists previously believed all life relied on sunlight. The discovery in 1977 shattered that fundamental assumption. Geologists aboard the submersible Alvin found something impossible. They observed dense clusters of life at extreme depths. The coordinates were 0 degrees 48 minutes north. The longitude was 86 degrees 5 minutes west. At 2,500 meters down, sunlight never penetrates. The ambient water temperature remains near 2 degrees Celsius. Yet the hydrothermal vents foster incredible biological density. This location is special because of its extreme isolation. It functions like an oasis in a barren desert. The surrounding abyssal plain is mostly devoid of life. Food usually falls from the distant ocean surface. Marine snow provides very little energy for deep creatures. The Galapagos Rift defies this standard biological rule entirely. Life here generates its own energy from the Earth. This remarkable process is known scientifically as chemosynthesis. Chemical energy replaces solar energy in this dark realm. Hydrogen sulfide flows steadily from the fractured oceanic crust. This chemical is highly toxic to most terrestrial animals. However, specialized bacteria thrive on this exact compound. Microbiologist Holger Janisch studied these unique microorganisms extensively. He realized they form the base of the food web. These microbes oxidize hydrogen sulfide to produce organic carbon. They multiply rapidly in the warm hydrothermal vent fluids. Some bacteria form thick white mats on the basalt. Others float freely in the shimmering thermal plumes. This bacterial production mirrors plant growth on dry land. Primary consumers feed directly on these microbial populations. The energy flow moves upward through a complex network. Filter feeders constantly siphon the microbe-rich vent water. The most famous residents here are the giant tube worms. Taxonomists officially named this unique species Riftia pachyptela. These large worms lack both a mouth and a stomach. For years, their feeding mechanism baffled marine biologists. Scientist Colleen Cavanaugh eventually solved this profound biological mystery. She discovered a specialized internal organ called the trophosome. Billions of symbiotic bacteria live inside this dark tissue. The tube worm absorbs hydrogen sulfide through its red plume. Hemoglobin in the blood transports the chemicals inward. The internal bacteria receive these essential raw materials. In return, The microbes synthesize sugars for the worm. This elegant symbiosis drives the entire vent ecosystem. Riftia grows incredibly fast under these specific conditions. Some individuals reach lengths of over 2 meters. Their white chitinous tubes provide shelter from harsh currents. They dominate the immediate area around the warm springs. These dense thickets create a microhabitat for other species. Giant clams also inhabit the cracked basalt pillars. Scientists classify these enormous bivalves as Galapagos magnifica. They nestle deep within the crevices of the rift. These clams also rely on internal symbiotic bacteria. Their gills house massive colonies of sulfur oxidizing microbes. A specialized foot extends down into the vent fluid. It absorbs sulfides directly from the warm water flow. The clam blood is rich with specialized binding proteins. This prevents the toxic sulfide from poisoning the animal. These bivalves can grow up to 30 centimeters long. Vent mussels attach themselves to the bare volcanic rock. Researchers identify these specific mussels as Bathymodiolus thermophilus. They possess a slightly different survival strategy here. These mussels maintain symbiotic bacteria in their delicate gills. However, they also retain a fully functional digestive system. They can actively filter feed from the surrounding water. This dual strategy provides excellent resilience against changing conditions. Vent fluid flow can shift abruptly due to earthquakes. Mussels survive these temporary disruptions better than giant clams. The food web expands outward from these primary consumers. Numerous grazers slowly patrol the extensive bacterial mats. Limpets scrape the microscopic life directly from the rocks. Small snails glide across the hardened lava formations. Galapagos vent crabs scurry among the towering tubeworm clusters. These pale crustaceans are known as Bythagria thermodron. They act as both aggressive scavengers and active predators. The crabs tear pieces of flesh from damaged tubeworms. They also consume the dying mussels near the periphery. Their eyes are severely reduced in this lightless environment. Squat lobsters represent another common scavenger at the rift. They possess long claws for reaching into narrow crevices. These white crustaceans closely resemble small, flattened crabs. They sift through the debris falling from the tubeworms. Energy flows efficiently from the bacteria to these scavengers. Higher up the food chain, true apex predators emerge. Vent octopuses glide silently above the hydrothermal chimneys. They use their sensitive tentacles to probe the darkness. These cephalopods hunt the abundant crabs and squat lobsters. Their soft bodies easily withstand the immense hydrostatic pressure. Zooarcid fish slowly navigate through the shimmering vent fluid. Researchers commonly refer to these elongated creatures as eelpouts. They measure about 30 centimeters in total length. Eelpouts feed primarily on small amphipods and vent snails. They exhibit a sluggish swimming style to conserve energy. The warm water allows their metabolism to function efficiently. Outside the vent plume, the freezing water slows them down. This sharp temperature gradient strictly limits their geographical range. They rarely venture far from the active hydrothermal vents. The Galapagos Rift ecosystem displays an astonishing biomass density. Scientists frequently compare it to a lush tropical rainforest. The surrounding deep ocean floor is comparatively barren. Standard abyssal plains support very few living organisms. A square meter of standard seafloor holds minimal life. A square meter at the vent holds thousands of organisms. The sheer volume of biological matter is truly staggering. This stark contrast highlights the immense power of chemosynthesis. Solar energy supports life on the bright Earth's surface. Geothermal energy supports life in this deep oceanic trench. The primary chemical reaction involves oxidizing dissolved hydrogen sulfide. Oxygen from the surrounding seawater mixes with the vent fluids. Microbes facilitate this specific chemical reaction to release usable energy. This energy allows them to convert carbon dioxide into cellular material. The process requires precise environmental conditions to function properly. The mixing zone between hot and cold water is crucial. If the water is too hot, the delicate enzymes denature instantly. If the water is too cold, the chemical reactions slow down. The organisms must carefully position themselves within this narrow gradient. Tube worms constantly adjust their red plumes to find the perfect balance. The Galapagos Rift differs slightly from other hydrothermal vent fields. Vents on the East Pacific Rise often feature towering black smokers. Those structures emit extremely hot fluids filled with dark iron sulfides. The Galapagos vents primarily consist of much lower temperature white smokers. These gentler springs emit fluids rich in barium and calcium. The maximum temperature here reaches roughly 350 degrees Celsius. Many of the vents gently weep fluid at much lower temperatures. This creates broad areas of diffuse flow across the fractured basalt. These extensive diffuse zones support the massive beds of giant clams. The relatively calm water flow prevents delicate larvae from washing away. Larval dispersal is a critical component of this unique ecosystem. Individual vent structures rarely remain active for more than several decades. Earthquakes frequently alter the subterranean plumbing of the oceanic crust. Old vents suddenly dry up and completely stop flowing. When the hydrogen sulfide disappears, the local ecosystem rapidly collapses. The tube worms and clams eventually starve without their symbiotic bacteria. Therefore, these organisms must constantly send offspring into the currents. Microscopic larvae drift through the cold, dark ocean for many miles. They must locate a newly formed vent to settle and grow. Scientists still study how these tiny creatures navigate the vast darkness. Some researchers believe the larvae detect faint chemical trails. Others suggest they follow subtle temperature gradients in the deep currents. The successful colonization of a new vent happens surprisingly fast. Within a few years, a barren rock becomes a thriving community. Microbes arrive first to establish the foundational bacterial mats. Small scavengers soon follow to graze on the fresh microbial growth. Tube worm larvae settle next and begin their rapid vertical expansion. The giant clams and mussels arrive later as the community matures. This predictable ecological succession mirrors the recovery of a burned forest. The Galapagos Rift provided the first direct observation of this cycle. The discovery of this ecosystem expanded the known boundaries of life. It forced scientists to reconsider the requirements for biological habitation. Before 1977, textbooks stated that all food webs required sunlight. The deep ocean was considered a vast, nutrient-poor biological desert. The Alvin submersible dives completely rewrote these fundamental scientific principles. Researchers Robert Ballard and Jack Corliss documented this impossible oasis. They collected physical samples that stunned the global scientific community. Biologists spent decades analyzing the preserved specimens from these early expeditions. The unique anatomy of the vent creatures required entirely new classifications. Whole new families of marine invertebrates were added to scientific registries. The energy flow at the Galapagos Rift remains incredibly efficient. Very little organic matter goes to waste in this closed system. When a giant tube worm dies, its casing is quickly broken down. Specialized bone-eating worms consume the remaining organic material within days. Even the empty clam shells provide hard surfaces for new larvae. The dissolved minerals from the vents constantly replenish the chemical supply. This continuous geological process ensures a steady input of raw energy. The ecosystem functions entirely independent of the distant solar cycle. Day and night have absolutely no meaning at this extreme depth. The seasons do not affect the constant flow of hydrothermal fluids. This independence makes the Galapagos Rift ecosystem remarkably stable over time. Surface events like hurricanes or algal blooms never reach these depths. The only significant disruptions come from violent geological upheavals below. Magma chambers shift deep within the Earth to alter the landscape. Fresh lava flows occasionally pave over established biological communities. Yet life always finds a way to return to the rift. The resilience of these deep-sea organisms continues to fascinate marine biologists. They endure pressures exceeding 250 atmospheres daily. They process toxic heavy metals that would instantly kill surface marine life. Their cellular structures have perfectly adapted to this extreme, hostile environment. The study of this ecosystem also influences the search for extraterrestrial life. Astrobiologists look closely at the Galapagos Rift for important clues. The icy moons of Jupiter and Saturn possess subglacial liquid oceans. Europa and Enceladus might harbor similar hydrothermal vent systems beneath their ice. If life can thrive in the dark oceans of Earth, it might exist there. The chemosynthetic bacteria of the rift prove that sunlight is not mandatory. Geothermal heat and chemical gradients are sufficient to sustain complex food webs. This realization broadens our understanding of habitable zones in space. The tube worm represents a completely alternative path for biological evolution. Our planet holds alien worlds beneath the crushing ocean waves. The year 1977 forever changed marine biology. Scientists boarded the research vessel Nord during late winter. They sailed toward the remote Galapagos Rift fracture zone. The target coordinates were 0 degrees 48 minutes north. Longitude stood precisely at 86 degrees 5 minutes west. Geologist Jack Corliss led the primary scientific diving team. Robert Ballard managed the advanced underwater camera sled operations. They sought the source of subtle deep ocean temperature anomalies. Previous surface ships had recorded strange thermal spikes here. No one expected to find a thriving biological community below. The team deployed the heavy Angus camera sled into darkness. This robust steel frame carried thousands of color film exposures. It hovered carefully just meters above the jagged basaltic seafloor. Acoustic transponders guided the heavy sled through the pitch black. Sensors detected a sudden ambient temperature rise of several degrees. Photographic film was quickly developed in a specialized shipboard darkroom. The resulting images revealed dense clusters of massive white clams. This stunning visual evidence prompted the deployment of submersible Alvin. 3 brave men climbed inside the cramped titanium pressure sphere. Alvin slowly descended 2,500 meters into darkness. The initial descent took over 90 minutes through freezing water. External water temperatures dropped rapidly to a chilling 2 degrees. Pilot Jack Donnelly carefully navigated the steep and dangerous ridges. Corliss and Tiered Van Andel peered through thick acrylic viewports. They observed shimmering warm water rising directly from rocky cracks. The external thermometer registered 17 degrees Celsius near the vents. This warm water provided a stark contrast to the cold. Giant red tube worms swayed gently in rising thermal currents. The scientists lacked proper biological sampling gear for these creatures. They improvised by using standard geological tools to collect specimens. News of this incredible discovery spread rapidly across the globe. Marine biologists organized a dedicated return mission in 1979. The research vessel Gillis served as the primary surface support. Microbiologist Holger Janisch joined the expert team to study microbes. Scientist J. Frederick Grassel focused intensely on diverse benthic animals. Biologist Ruth Turner analyzed the rapid growth rates of bivalves. Engineers upgraded Alvin with highly specialized biological sampling equipment. They installed delicate manipulator arms and insulated sample collection boxes. A newly designed suction device captured fragile swimming organisms safely. This specific expedition mapped a famous vent site named Rose Garden. The Rose Garden site became a primary focus for observation. Scientists left physical titanium markers to carefully track future changes. They deployed passive temperature probes directly into flowing vent streams. These advanced probes recorded continuous thermal data for many months. Acoustic release mechanisms allowed expensive instruments to float safely upward. Researchers meticulously measured fluid flow rates emerging from fractured basalt. Chemical sensors tracked dissolved hydrogen sulfide concentrations in the water. The team collected hundreds of pristine water samples using bottles. Heavy pressure vessels maintained extreme deep sea conditions during ascent. This careful process preserved delicate microbial communities for laboratory analysis. Deep sea exploration technology advanced significantly throughout the 1980s. New multibeam sonar systems provided incredibly detailed topographic rift maps. Scientists identified distinct geological fault lines shaping the spreading center. Remotely operated vehicles began to supplement traditional man-submersible dives. The ROV Jason offered extended observation times without human fatigue. Long fiber optic cables transmitted high-definition video to the surface. Researchers could now watch bustling vent ecosystems in real time. Automated chemical analyzers were deployed directly onto the rugged seafloor. These devices performed complex chemical titrations at extreme hydrostatic pressures. Valuable recorded data was stored securely inside thick glass spheres. A major return mission in 1985 revealed changes. The once vibrant Rose Garden site showed clear decline signs. Large mussel populations had completely overgrown the giant tube worms. Vent fluid temperatures had dropped by several degrees since discovery. This evidence proved that hydrothermal ecosystems were highly dynamic environments. Subsequent expeditions in the early 90s focused on tectonic movements. Scientists used sensitive tilt meters to measure subtle oceanic crust deformations. Ocean bottom seismometers recorded hundreds of micro-earthquakes along the valley. These constant tremors indicated molten magma shifting beneath the floor. Such underlying geological activity directly controlled the hydrothermal vent lifespan. The year 2002 marked the 25th anniversary. Scientist Stephen Hammond led a comprehensive survey of the rift. The dedicated team searched tirelessly for the original rose garden. They towed a sophisticated digital camera system across historical coordinates. A massive fresh lava flow had completely paved over the area. The previously thriving biological community was buried under black rock. This dramatic geological event highlighted the violent deep seafloor nature. However, the diligent scientists soon discovered a brand new vent. They officially named this nascent hydrothermal ecosystem the Rosebud Site. The Rosebud location featured very young tube worms beginning growth. Biologists eagerly sampled newly established pioneer species at the site. They desperately wanted to understand how life colonized volcanic rock. Modern genetic sequencing tools allowed precise identification of new microbes. Researchers discovered completely unique strains of floating chemosynthetic bacteria. These microscopic organisms formed thick white microbial mats on basalt. Autonomous underwater vehicles systematically mapped the area with multibeam sonar. The AUV named ABE flew precise automated grid patterns above. It generated incredibly high-resolution bathymetric charts of the eruption. Sensitive chemical sensors on the AUV sniffed out fluid plumes. This automated robotic approach vastly increased deep ocean exploration efficiency. Another highly significant major research cruise occurred in 2005. The famous submersible Alvin completed its 2000th career dive. Scientists focused their intense efforts on the deeper western portion. They explored extreme depths exceeding 3,000 meters in darkness. The crushing ambient pressure reached 300 atmospheres quite easily. Researchers deployed specialized acoustic modems to transmit digital ocean data. These clever devices allowed submerged instruments to communicate with ships. Permanent long-term monitoring stations were successfully established at vents. Automated time-lapse cameras captured fascinating daily rhythms of crabs. Sensitive current meters recorded highly complex deep ocean tide patterns. The advanced NOAA ship Okeanos Explorer arrived in 2011. This modern mission utilized a state-of-the-art telepresence system. Dedicated satellite links broadcast live video to shore-based scientists. Researchers around the globe participated in deep dives simultaneously online. The ROV Little Hercules explored the dark rift with lights. They soon discovered a massive silent field of dead clams. This haunting fossilized community stretched for hundreds of rocky meters. It provided a permanent historical record of past venting activity. Scientists carefully measured the isotopic composition of ancient carbonate shells. These specific chemical signatures revealed precise ancient vent fluid temperatures. Modern scientific expeditions rely heavily on autonomous remote sensor arrays. Complex mass spectrometers are now safely pressure-housed for deployment. They continuously analyze dissolved vent gases like methane and carbon. Advanced optical sensors constantly measure the turbidity of rising plumes. Acoustic Doppler current profilers accurately map upward fluid vertical velocity. These durable scientific instruments remain actively working for 2 years. Corrosion-resistant titanium metal protects highly delicate internal electronic components. High-capacity lithium battery packs provide reliable power in freezing depths. Crucial data recovery missions occur during brief calm weather windows. Scientists must carefully clean thick biological fouling from sensor lenses. Marine geologists also conduct extensive deep crustal drilling operations nearby. The massive drilling vessel JOID's Resolution extracts long rock cores. These dense basalt cores reveal fascinating ancient magnetic seafloor history. Iron-rich minerals inside the rock align perfectly with Earth. Researchers closely analyze intense chemical alteration caused by geothermal water. Glittering veins of quartz and golden pyrite trace plumbing systems. Precise isotope geochemistry helps determine the exact geological crustal age. The Galapagos Rift slowly spreads at 50 mm per year. This moderate tectonic spreading rate creates a distinct ridge morphology. Steep fault scarps expose deep structural layers of the lithosphere. Biological sampling techniques have evolved significantly since those early days. Early collection nets often severely damaged fragile deep-sea creatures. Modern ROVs now use gentle suction samplers with silicone hoses. Automated rotary carousels sort biological specimens into isolated acrylic chambers. Pressurized and insulated bio-boxes keep collected animals alive on board. Scientists carefully extract cellular DNA to build comprehensive phylogenetic trees. They closely compare Galapagos vent species with East Pacific ones. Specialized larval traps capture tiny microscopic organisms drifting freely around. This crucial data helps explain how isolated vent communities spread. Harmless fluorescent chemical dyes accurately track complex water movement patterns. The ongoing scientific study of the rift is a global effort. Dedicated researchers from numerous countries share vital open access data. Major oceanographic institutes collaborate closely to fund expensive exploration missions. The Interridge Science Program coordinates international studies of spreading centers. Strict standardized measurement protocols ensure perfect data compatibility across cruises. Scientists regularly publish detailed findings in respected marine biology journals. Each new expedition firmly builds upon vast knowledge gathered previously. The Deep Rift remains an absolutely critical natural marine laboratory. It constantly provides profound new insights into early life origins. Astrobiologists intensely study these vents to understand extraterrestrial ocean worlds. The profound legacy of the 1977 discovery endures. The original Alvin submersible has been completely rebuilt multiple times. It now features a larger titanium sphere and improved visibility. High-definition digital cameras have entirely replaced old photographic film. Brilliant LED lighting arrays easily pierce the eternal ocean darkness. The dynamic Galapagos Rift continues to surprise scientists with discoveries. Many uncharted and pristine hydrothermal vent fields likely remain hidden. Deep ocean currents constantly shift complex thermal energy distribution patterns. Future scientific expeditions will eventually deploy advanced autonomous robotic swarms. These intelligent machines will monitor active rifts continuously without humans. The autonomous underwater vehicle Sentry remains a marvel of engineering. Its highly aerodynamic shape allows it to glide incredibly efficiently. Sentry mapped the Galapagos Rift with unprecedented high-resolution sonar. It successfully revealed tiny geological fissures that older ships missed. The robotic vehicle hovers exactly 50 meters above volcanic terrain. Side-scan sonar continuously paints detailed acoustic pictures of darkness. Sensitive magnetometers detect incredibly subtle local magnetic field strength variations. Sentry operates completely independently of the distant surface support vessel. It follows complex pre-programmed navigational waypoints using advanced Doppler logs. Upon completing its scientific mission, it drops a weight safely. The incredible scientific journey at the Galapagos Rift continues onward. Every single deep dive reveals another hidden secret down below. The steady, comforting hum of research vessels echoes softly above. Far below, quiet scientific instruments stand vigil in silent currents. They continuously record the slow thermal heartbeat of volcanic Earth. Digital data flows upward through miles of dark, freezing water. Scientists quietly watch glowing computer monitors in dimly lit rooms. The relentless pursuit of scientific knowledge continues in this frontier. The Galapagos Rift remains a lasting monument to human curiosity. Its wondrous hydrothermal vents will fuel pure scientific wonder forever. The Galapagos Rift represents just one type of hydrothermal environment. Scientists constantly compare this site to other oceanic ridges. The Mid-Atlantic Ridge features much deeper and hotter vent systems. Water temperatures there can exceed 400 degrees Celsius. Galapagos vents typically emit fluids around 35 degrees Celsius. This stark temperature difference creates completely distinct biological communities. Atlantic vents host vast swarms of pale blind shrimp. Pacific systems like the Galapagos feature giant tube worms. These evolutionary paths diverged millions of years ago. Ocean currents act as slow highways for microscopic larvae. Larval dispersal dictates which species colonize new volcanic fissures. The East Pacific Rise sits further west from the Galapagos. Vents along that ridge grow massive sulfide chimneys rapidly. Galapagos structures remain relatively small and close to the seabed. The Mariana Back-Arc Basin contains vents nearly twice as deep. Pressure at those western Pacific sites crushes standard research equipment. Galapagos fluid chemistry leans heavily toward hydrogen sulfide concentrations. Other global sites emit higher levels of dissolved iron. Indian Ocean vents feature strange scalefoot snails with iron armor. No such armored mollusks exist along the Galapagos Rift. Geographic isolation shapes these dark abyssal ecosystems quite profoundly. Researchers view the Galapagos Rift as a biological time machine. These warm fissures might hold clues to early planetary life. A billion years ago, Earth lacked a protective ozone layer. Surface radiation would have destroyed fragile organic molecules instantly. The deep ocean provided a dark shield against ultraviolet destruction. Hydrothermal fluids carry essential raw materials for cellular development. Carbon dioxide and hydrogen mix within the heated crustal rocks. This geological mixing generates simple organic compounds without sunlight. Scientists refer to this process as abiotic organic synthesis. Dr. John Corliss first proposed this origin theory here. His 1977 observations changed our understanding of astrobiology forever. Alkaline hydrothermal vents offer another piece of the biological puzzle. The Galapagos Rift features slightly acidic fluid emissions. However, nearby off-axis systems demonstrate high alkaline fluid properties. Serpentinization occurs when seawater reacts with exposed mantle peridotite. This chemical reaction naturally releases significant amounts of hydrogen gas. Hydrogen acts as a potent fuel source for primitive microbes. Microscopic pores within vent chimneys resemble early cellular membranes. These rocky compartments could trap complex molecules together. RNA strands might have formed within these microscopic mineral walls. The temperature gradients provide constant energy for chemical reactions. Life perhaps began in the dark warmth of the abyss. This profound realization extends far beyond our own planet. The Galapagos Rift serves as an analog for alien oceans. Jupiter possesses an ice-covered moon known as Europa. Saturn orbits with a tiny frozen moon called Enceladus. Both celestial bodies hide vast liquid oceans beneath their ice. Gravitational friction heats the rocky cores of these distant moons. This internal heat likely generates alien hydrothermal vent systems. Space probes have detected silicon nanoparticles erupting from Enceladus. These particles strongly suggest active hot springs on the seafloor. Tube worms thrive in the dark waters of the Galapagos. Perhaps similar microbial ecosystems survive in the outer solar system. Exploring the Galapagos Rift requires overcoming immense engineering hurdles. The crushing pressure at 2,500 meters is unforgiving. Water presses down with thousands of pounds per square inch. Submersible hulls must withstand continuous structural compression and expansion. The titanium sphere of Alvin measures barely 2 meters across. Engineers machine these metal spheres to microscopic tolerances. A tiny structural flaw would cause instantaneous catastrophic implosion. Total darkness presents another significant challenge for deep-sea navigation. Light simply cannot penetrate these profound oceanic depths. Research vessels rely on powerful acoustic sonar to map terrain. Sound waves bounce off the jagged basaltic lava formations. Salt water acts as a highly corrosive agent on electrical components. Vent fluids contain dissolved minerals that quickly coat camera lenses. The extreme temperature gradients stress external scientific instruments severely. Water at the vent opening might be 300 degrees. Just 1 meter away, the ambient ocean sits near freezing. This rapid thermal shock shatters ordinary glass and brittle plastics. Remotely operated vehicles depend on long fiber optic tether cables. These vital cables span thousands of meters through ocean currents. Managing tether tension requires constant vigilance from the surface crew. A snagged cable on a rocky chimney spells disaster. Radio waves cannot travel through thick layers of seawater. Manned submersibles must communicate using slow acoustic telemetry systems. Data transmission rates resemble early dial-up internet connections. Sending a single low-resolution photograph takes several minutes. Power constraints limit the duration of every scientific dive. Heavy silver-zinc batteries once powered the early Alvin expeditions. Modern vehicles utilize advanced lithium-ion battery modules for endurance. Even with modern power, dives rarely exceed 10 hours. The descent and ascent consume nearly 4 hours alone. Scientists possess only a brief window for actual seafloor observation. The Galapagos Rift generates vast deposits of valuable minerals. Superheated fluids dissolve metals from deep within the oceanic crust. When this fluid hits cold seawater, the metals instantly precipitate. These precipitating particles slowly build massive polymetallic sulfide deposits. These underwater structures contain high concentrations of copper and zinc. Significant amounts of gold and silver also accumulate here. The global demand for these specific raw materials is surging. Technology companies require rare earth elements for modern electronics. Electric vehicle batteries rely heavily on cobalt and manganese. Terrestrial mines are slowly depleting their easily accessible ore reserves. Mining corporations now look toward the dark abyssal plains. Mineral wealth represents only one facet of hydrothermal resources. Biological prospecting offers immense potential for pharmaceutical advancements. Extremophile bacteria possess unique enzymes adapted to harsh conditions. These microbial proteins remain stable at boiling temperatures. Industrial manufacturing processes frequently require heat-resistant chemical catalysts. DNA amplification techniques already utilize enzymes from hot spring bacteria. Deep-sea microbes might hold cures for dangerous human pathogens. Scientists isolate novel antibiotic compounds from vent-dwelling organisms. Marine sponges and soft corals produce complex defensive chemicals. These natural toxins occasionally show remarkable anti-cancer properties. The genetic resources of the Galapagos Rift remain largely unexplored. Extracting these deep-sea resources poses severe environmental risks. Commercial mining machines would obliterate fragile vent structures completely. Massive robotic cutters would grind the sulfide chimneys into dust. This destructive process would instantly kill the stationary tube worms. Plumes of toxic sediment would drift for hundreds of miles. Suspended rock particles would choke delicate filter-feeding organisms. Heavy metals released into the water column poison marine food webs. The noise from mining operations disrupts whale communication channels. Deep-sea ecosystems grow and recover at incredibly slow rates. A destroyed vent community might take centuries to regenerate fully. The International Seabed Authority regulates mining in international waters. The Galapagos Rift falls partially within Ecuador's exclusive economic zone. Ecuador established the massive Galapagos Marine Reserve for protection. This marine sanctuary shields thousands of square kilometers of ocean. However, boundaries blur in the vastness of the Pacific. Ocean currents carry pollutants across invisible political borders effortlessly. Conservationists advocate for a global moratorium on deep-sea mining. They argue we know too little about these abyssal ecosystems. Scientific research must precede any commercial extraction efforts. Preserving the Galapagos Rift honors its historical scientific significance. Let us return to the biological differences across the globe. The Galapagos Rift lacks the swarming crabs of the Atlantic. Instead, brittle stars blanket the basaltic rocks in dense mats. Pacific vents host the iconic Riftia pachyptela tube worms. These red-tipped worms can grow over 2 meters long. Atlantic vents feature the Rimicaris exoculator blind shrimp species. These shrimp cultivate bacteria on their specialized gill structures. Indian Ocean vent fields introduce entirely different evolutionary novelties. The scalefoot gastropod incorporates iron sulfide into its actual shell. This metallic armor protects the snail from predatory crabs. No other known animal builds a skeleton from iron. Spreading rates dictate the geological character of a ridge. The Galapagos Rift represents an intermediate spreading ridge system. Tectonic plates pull apart at roughly 6 centimeters per year. The East Pacific rise spreads much faster by comparison. Those plates separate at nearly 15 centimeters annually. Fast-spreading ridges create smooth volcanic profiles across the seafloor. The Mid-Atlantic ridge spreads slowly at 2 centimeters yearly. Slow ridges feature deep central rift valleys and steep mountains. The intermediate Galapagos Ridge displays characteristics of both extremes. It features a shallow axial valley with frequent volcanic eruptions. These eruptions pave the seafloor with fresh glassy basalt. Chemosynthesis forms the foundation of all vent ecosystems globally. This metabolic pathway might reflect the earliest forms of life. Ancient microbes likely consumed hydrogen and carbon dioxide directly. This primitive metabolic process is scientifically known as methanogenesis. Methanogens still thrive within the deep rocks of the Galapagos. They produce methane gas as a natural biological byproduct. Some scientists argue life started with simple metabolic cycles. Chemical networks formed before complex genetic molecules like DNA. The warm alkaline fluids provided a steady flow of reactants. Iron and sulfur minerals acted as natural catalysts for reactions. The Galapagos rocks contain the exact minerals needed for this. Future exploration of the Galapagos Rift requires new autonomous technologies. Autonomous underwater vehicles can map the seafloor without human pilots. These robotic torpedoes glide silently above the volcanic terrain. They carry high-resolution multibeam sonar and sensitive chemical sniffers. Chemical sensors detect faint traces of hydrogen sulfide in water. This chemical trail leads researchers to undiscovered vent fields. Machine learning algorithms process the vast amounts of sonar data. Artificial intelligence can identify potential hydrothermal chimneys automatically. New materials will allow submersibles to dive even deeper safely. Ceramic pressure housings offer lighter alternatives to heavy titanium spheres. These advancements will eventually unlock the remaining abyssal mysteries. The rocky crust beneath the Galapagos Rift hides another secret. A massive subterranean biosphere exists deep within the fractured rock. Microbes live miles beneath the ocean floor in solid basalt. They survive on the faint chemical energy of the rocks. These deep earth organisms reproduce at astonishingly slow rates. A single cell division might take hundreds of years. This sluggish metabolism pushes the known limits of biology. Studying these organisms requires drilling deep into the oceanic crust. Specialized drill ships carefully extract long cylindrical rock cores. Scientists examine these basalt cores in sterile laboratory environments. Contamination from surface bacteria would ruin the delicate samples completely. Global climate change also threatens these remote abyssal ecosystems indirectly. The deep ocean absorbs massive amounts of atmospheric carbon dioxide. This absorption slowly increases the overall acidity of seawater globally. Ocean acidification dissolves the delicate shells of deep-sea mollusks. Warming surface waters alter the global ocean circulation patterns. Deep ocean currents transport vital oxygen to the abyssal plains. Changes in these currents could suffocate deep benthic communities. The Galapagos Rift relies on these steady nutrient streams. Even at 2,500 meters, the ocean remains entirely interconnected. Human actions on the surface ripple down into the darkness. Protecting the climate ultimately protects the deep hydrothermal vents. Microbial diversity varies drastically between different global ridge systems. The Galapagos Rift harbors unique strains of sulfur oxidizing bacteria. These specific strains differ genetically from those in the Atlantic. Environmental factors drive this rapid microscopic evolutionary divergence. Temperature fluctuations force bacteria to adapt their enzymatic structures constantly. Some microbes form thick white mats across the basaltic rocks. Scientists refer to these bacterial formations as microbial snow. Deep ocean currents sweep this biological snow across the seafloor. Filter-feeding organisms rely entirely on this drifting bacterial nourishment. Comparing these microbial populations reveals the complex history of oceans. The legacy of the Galapagos Rift continues to inspire scientists. Dr. Robert Ballard and his team opened a new frontier. Their 1977 discovery fundamentally shifted our perspective on biology. We now view the deep ocean with profound new respect. It is not a barren wasteland of crushing dark water. It is a vibrant cradle of extreme and resilient life. The technological challenges of exploring this realm remain formidable. Yet human curiosity drives us to build better submersibles constantly. We must balance our thirst for resources with ecological preservation. The deep sea demands our careful stewardship and patient understanding. The Galapagos Rift continues its quiet existence in the dark. Far below the sunlit waves, the tectonic plates slowly separate. Magma heats the cold seawater in an endless geological rhythm. Giant tube worms sway gently in the warm chemical currents. Giant clams filter the mineral-rich water without ever seeing light. This hidden world operates perfectly without any human intervention today. It is a realm of extreme pressure and absolute darkness. Yet it is filled with vibrant, thriving, and complex life. The ocean holds these ancient secrets in its deep embrace. Our submersibles bring fleeting moments of light to the abyss. When the floodlights turn off, the eternal darkness returns immediately. The creatures of the rift continue their slow biological cycles. They live in perfect harmony with the violent volcanic forces. This remote ecosystem reminds us of the beauty of nature. There are still undiscovered frontiers right here on our planet. The deep sea invites us to maintain our quiet curiosity. It teaches us to respect the hidden depths of Earth. The mysteries of the abyss will wait for future generations. Now, let your mind drift away from the deep ocean. Leave the warm hydrothermal vents behind in the peaceful dark. Imagine the gentle rise through the calm, quiet water column. The immense pressure of the deep sea slowly fades away. You float upward through the cool, silent pelagic ocean zones. You feel completely weightless as you drift toward the ocean surface. The gentle rocking of the ocean waves lulls you into deep relaxation. Every muscle in your body releases tension into the cool ocean water. The soothing sounds of the sea guide you toward a restful slumber. Gentle ocean currents carry away all of your daily thoughts. Your breathing perfectly matches the slow rhythm of the tides. The surface of the ocean is calm and beautifully still. The journey to the Galapagos Rift is now fully complete. Your mind is as vast and tranquil as the sea. Rest now in the comforting embrace of the quiet night. Let the silence of the deep ocean bring you peace. Thank you for watching this peaceful deep ocean documentary tonight. May you have a restful sleep and very sweet dreams.